And so checking out our view, the intermolecular forces that act between molecules of HBr, these are London forces and dipole-dipole forces. And looks like maybe one of you missed the dipole-dipole forces here. And that is, dipole-dipole forces are also present. In fact, the two different types are present because HBr, what type of molecule is HBr? Polar or nonpolar? Got a clue there, Jeremy? That's a polar one. It's a polar. And so that, in order to have answered it, you would need your table of electronegativities. So we would have seen the hydrogen is at 2.1, bromine is at, I think, 2.8. And so if we look those up, we'd see there's a difference in electronegativity. If one's more electronegative than the other, then it's going to be a polar molecule. If it's a polar molecule, it would have dipole-dipole forces. And all molecules have London forces. So any questions on that one? Okay, then our second one, hydrogen bonding acts between which of the following molecules? If necessary, refer to the models up here on the front bench. Correct answer in this one is ethanol, and that's this one. And what do we look for? What does this one have that this one does not have? Right, so we look for hydrogen connected to an oxygen on this one. That makes this a very polar bond right here. And when the hydrogen is directly connected to nitrogen, oxygen, or fluorine, then hydrogen bonding is present. These molecules of ethanol are going to have a strong attraction for each other. All right, so with that said, here's where we're at today. We have a test scheduled, exam 4. That one is going to be on D2L. It's going to run from 6 o'clock on Tuesday through Thursday midnight. The exam itself, you'll have 60 minutes to complete the exam. It's going to cover chapters 18 on organic chemistry, chapter 12 on intermolecular forces and solids and liquids and such. And then it picks up another component of chapter 10, which was on electronegativity and molecular polarity. And then we'll also include chapter 13, which is what we're covering here today. We do have the extra credit opportunity. Talked about last week, it's the experiment. I saw that somebody's already turned that in. And it will take 3 days, even though it itself, probably it only takes about an hour to 2 hours of actual time. It does have to be spread out over a period of 3 days in order for you to make your observations. Any questions on what is coming up for your expectations? All right. Now, of course, because this is a hybrid course, we're not covering everything in here in the lecture portion. Ordinarily, we spend a lot more time with this. So these are going to be some terms that you are expected to know. I'll post all this here on D2L Brightspace. What we're going to do here today is we're going to spend time with these 4 in this first hour, and then I have some demonstrations related to these. So we're going to start up then again by working with these 4, and we'll start by defining a saturated solution. And again, the rest of those terms on there are your responsibility to work with. We talk about a saturated solution. We say that a saturated solution is one that contains the maximum amount of solute that will dissolve in a specified amount of solvent at a given temperature. So just like when we talked about the term saturated, when we were referring to hydrocarbons, the term saturated means that it's full of something. In this case, a saturated solution is going to be full of solute. It cannot hold any more solute at a given temperature. The other thing that we want to look at here is that this definition specifies 3 different variables. This is a 3-variable definition. It's the amount of solute, the amount of solvent, and the temperature. So again, this is a 3-variable definition. Depends on 3 things. So that means that when we get to an unsaturated solution, as its name would suggest, an unsaturated solution is going to be one that contains less than the maximum. And we actually define it based on a saturated solution. We say that it is one that contains less dissolved solute, contains less dissolved solute than a saturated solution at the same temperature. Morning. And then if we go to a supersaturated solution, a supersaturated solution is going to look like it's defined a whole lot like an unsaturated solution. Only difference is we change the word less to more. So we say that it's one that contains more dissolved solute than a saturated solution at the same temperature. So again, the distinction here is that an unsaturated solution is one that contains less dissolved solute. A supersaturated is one that contains more dissolved solute than a saturated solution. And it's the last one here that baffles a lot of people, especially if you've not seen this before, because we talk about a saturated solution as one that contains the maximum amount. How can we have more than the maximum? What we're going to do here is we're going to demonstrate a little bit about how that might be. So I brought out some demos here today, and we'll start by looking at these two, and I'll bring these out here a bit. These two solutions are solutions of sodium chloride, which of course sodium chloride is ordinary table salt. And if you look at each one of these, you should see that each one of them appears to be just one substance. When in fact, when we talk about a solution is a homogeneous mixture. And so simply by looking at this, you could not tell that each one of these is a mixture. Okay, but it is a mixture of sodium chloride and water. One of them though happens to be a saturated solution, one of them happens to be, look at that, happens to be an unsaturated solution. So what I'm going to do here is I'm going to pour some salt into each one of these. Whoa, not quite that. I'm not sure it does, because it really doesn't matter. I want to try to get relatively the same amounts added each one, so that's about the same. And then I'm going to take each one of these and I'm going to shake them up a bit. I'm going to try to get the stuff to dissolve in here and see what happens. I think that's probably good. So now if we want to look at a quick difference between them, what's happened in this one right here? It's dissolved. And in this one here, not dissolved. So if we had to determine whether this was saturated, unsaturated, or supersaturated, what would this one here be? This one's unsaturated because we're able to dissolve more solute. This one would have been saturated because it already was holding its maximum. If we try to put more solute into it, we couldn't do that. So now then the question would be is if I were to take this solution, we now see the salt that's in the bottom here, if I pour the liquid portion off of here, is the liquid portion going to be saturated, unsaturated, or super saturated? What do you think? I pour the liquid off. I think it's going to be saturated, unsaturated, or super saturated.
Super.
Are you going to make a commitment?
Saturated.
Saturated? What do you think? Super?
Super.
Super?
Super.
Super? Super? Who said saturated?
I did.
Yeah, just you?
Yeah.
Yeah, you're right. Yeah. Because if we go back to the definition here on this one, we say that the saturated solution is the one that contains the maximum amount. If we try to dissolve more into it, we can't dissolve any more into it. We try to put more into it, it's not going to take any more. But then the rest of you are going, well, wait a minute, he's got that one more definition up here that's super saturated. And the super saturated is the one that says it contains more dissolved solute. And again, the key here is it's more dissolved solute. When we added more in here, we couldn't dissolve anymore. It already had its maximum. So simply putting it in here is not going to make it supersaturated. Now, before I tell you how we make a supersaturated solution, what I'm going to do is I'm going to show you some supersaturated solutions. And this here happens to be a supersaturated solution. And this one happens to be one that is supersaturated with sodium acetate. And what I'm going to do here is I'm going to add some more sodium acetate to this. But before I do that, what I'm going to do here is I'm going to have each one of you just feel the flask so you can just feel its temperature. Just put your hand on the bottom. More. There we go. Okay, so you feel it. How does it feel? Room temp? Okay. So then what we're going to do here is I'm going to add some sodium acetate to this. Again, this is a super saturated solution. Again, it's super saturated with sodium acetate. And I'm going to add a little bit of sodium acetate to this. In fact, this little bit is going to be such a little bit. If I get this right. I think I have this right now. So I just want to show you how much sodium acetate I'm going to add. So how much you see in there? Seeing one crystal, right? So I'm going to add to this, let's see, just one little crystal. Got it? All right, so I'm going to take this one little crystal and I'm going to add to the sodium acetate, and we're going to watch what happens to this. Now, what do you think is going to happen when I try to dissolve it? This is super saturated now, which again is one that contains more solute than a saturated solution at the same temperature. Well, let's take a look. We'll drop into one. Oh, there must have been two on there. Okay, now, ain't that fun? I love this after all these years, I just do. Now, what do you think's happened to the temperature? Now, I would have this on Socratum, but you know each other now here. You shouldn't be embarrassed. How many think that the temperature increased? You have your choice of increase, decrease, or stay the same. So, how many think it increased? How many think it decreased? How many think it stayed the same? All right, let's go ahead and just feel this now. I always like doing this to see the facial expressions. Ain't that cool? So the temperature in this actually went up. Okay? So now, when we look at this, now I think in this particular class, we skipped it in here. This is part of a do on your own type of thing. But if I refer back to phase changes like you should have looked at on your own this past week, there's an energy diagram that I often like to write that looks something like this. It goes solid, liquid, gas, and I'm just writing them in increasing energy going up. So this is energy going up here. If we go in this direction right here, these phase changes are endothermic. And if we go in this direction right here, these phase changes are exothermic. So when a liquid goes into solid, it actually gives off energy. I say, wow, that doesn't make sense. Solid is at a lower temperature. Well, it has to make sense because in order to get to lower temperature, it has to give off energy to its surroundings. Usually, we look at the other process, if we think about it, it makes sense. If, for example, you put an ice cube in your hand, an ice cube in your hand is going to do what? It's going to melt. In order to melt, go from a solid to liquid, it has to absorb energy out of your hand, and your hand is going to get cold when that ice cube is absorbing energy out of the hand to go through that phase change. So just the reverse is true. When a liquid goes to solid, it gives off energy. Now this isn't quite a liquid going into solid. This is actually an aqueous, a dissolved material going into solid, but it shows pretty much the same thing here, the fact that we increase the temperature. Now can you think of any uses for something like this? What might we use this for?
Like heaters, like little, like to cook your food and stuff, or like hand warmers or something.
Yeah, we do, actually. And you didn't even see these up here, did you? Yeah, how about that? So what I have here, it turns out, lucky we have just 6 of you here today, and I have 7 of these, which means I get one of my own today. I usually don't get one of my own for demo, so I'm going to pass one of these out here to everyone. These are some portable hand warmers. And before you do anything with these, see, this is the advantage of a small class. Everybody gets their own little thing to play with. And what this is right here, this is a package that contains supersaturated sodium acetate. And on the inside of here, there's a small metal disc. And if you read the instructions on here, it'll tell you what you're going to do. You're going to gently bend the disc. So you go ahead and click on it if you want. Just press on that disc. You'll feel it snap. And once it snaps, you're going to see that the excess sodium acetate that is in solution winds up crystallizing out of solution. As it does, you can feel the pack get warm. Okay? So yeah, very good there, Simon. This is one application of these. And so, again, this is nothing more than a supersaturated sodium acetate solution. The whole purpose of the metal disc in there is to produce a seed crystal. And then that small disturbance in there, that click that you hear, causes a couple of the sodium and ascodines to come together. And once that seed crystal is formed, then the crystals then deposit out of solution. All the excess solute comes out of solution. It still feels soft in here because turns out there's still some water that's in here. So at this point now, if I could open and tear this package open, or I go to this solution here and shake it up a little bit, there's going to be some liquid that comes out of here. And if I squeeze that liquid out of there, the liquid that's going to remain in there is going to be a saturated solution. And what we've done is we've taken the excess solute out of the solution. Now, I don't think any of my colleagues are going to use this later today, but these are ones that we've used now for several semesters. If we want to use this again, what are we going to do with these? Well, I go back into my prep area there. I set up a pot of boiling water and throw these things in, and once I throw them in, the sodium acetate that's in here will redissolve. I cool them back down to room temperature, and then we can use them again. Same with these flask that I have right here, this particular one, I can use this one over and over and over again each semester, simply by heating it up until the sodium acetate dissolves and cooling it back down to room temperature. And that's kind of the whole key if we look at those definitions and why it's a 3-variable definition. We say it's the amount of solute per specified amount of solvent at a given temperature. And so if I change temperature, I can actually change the amount that will dissolve in there. Now many substances, when you cool them back down, if I heat it up and cool it back down, they're going to crystallize out on their own. Sodium acetate happens to be a one though that stays in solution when you cool it back down in there. So any questions on this one? Okay, you've probably seen other examples of supersaturated solutions. Honey is an example of a supersaturated solution. If honey sits on the shelf for a long period of time, what happens to it? Yeah, it begins to solidify. And that's the excess fructose coming out of the solution. Now, not a lot of people want to spread the crystallized sugar on their sandwiches. So if you want then to redissolve that sugar in the honey, what do?
Heat it up.
Heat it up. You heat it up, you redissolve the fructose in there, and then you have your nice supersaturated honey solution. And honey is nothing more than a supersaturated fructose solution. Another place you may have seen it, that my first exposure that I remember to supersaturated solutions was when I was in elementary school, and we make rock candy. I don't know if any of you have ever done that before, but you take some water and you dissolve some sugar into it. You might dump a whole bunch, I don't know what it is, it's maybe like 1 cup of sugar to 1 cup of water, which if you think of that amount of sugar is not going to dissolve in water. So how do you get the sugar to dissolve? You heat it up. You heat it up at higher temperature, you redissolve it, then you cool it back down to room temperature, and then you take a string, suspend it into the supersaturated sugar solution, maybe a seed crystal sugar on there, and then the sugar will crystallize out and form this rock candy around that seed crystal sugar that you place into it. So, anyhow, any questions on this? Questions? All right, I will take these back, and since we're talking about applications of these, first maybe you want to keep them cold.
No.
No? Okay. It's supposed to warm up this weekend. I saw the forecast. We got 60s on Sunday and Monday, and maybe even tomorrow. So we're in good shape. I'm bringing these out here as well. Now these have nothing to do actually with solutions, but I'm bringing them out there to show that there's different types of hand warmers out there. And this type of hand warmer this is the type that I use. And if you look on the back side of these here, this one tells what the contents of these are. And inside this one we have some iron powder, water, salt, activated charcoal, and vermiculite. And these now, I don't know if any of you use hand warmers. Have you ever used this type before? Have you used those? Okay. How many of you used this type before? Okay. Now, there's a difference between the two types. Now, it might depend upon what you want. This one, as you saw, you get instant heat. I mean, we snapped it, and like almost instantly you could feel the warmth coming off of it. How do you get the heat out of these? What do you need to do? Yeah, but first you need to open the package. And so in this case, the way that these work, if you remember these are the ones that kind of feel like they're a cotton bag. It's kind of a cloth bag. And so what the bag does in here, it allows for the passage of oxygen through the surface. And so when we look at the hand warmers here, I'll write these down here so you have some basis for these. Again, the first type of hand warmer was a supersaturated sodium acetate solution. So again, one was a supersaturated sodium acetate solution. And that's the one that actually pertains to what we're covering right now. But the one that you're looking at here is actually something that pertains to stuff that we've already covered in here. This is actually the only real active ingredient in here is the very first one on the list, and it is iron powder. And iron powder is exactly what it says it is. It's iron metal that we've ground up into a powder. And so what happens is that that iron powder, again, once we tear it open, that's going to expose it to oxygen, which you write as a formula of O2. And this is not a fancy reaction. What do we get when we combine iron and oxygen? It's going to be called iron oxide, exactly. Now what you might remember about iron is one of those transition elements, so that means it can have multiple charges, so we wouldn't know actually without some experience whether it's iron 2 or iron 3. I'm telling you it's iron 3 because I have the experience. And so this is going to be iron 3 oxide, and the formula for iron 3 oxide looks something like this right here. And I'm going to have to close this and reopen it. Something's happening to my... Alright, how do I get this? I don't have an Alt on here, do I? So I need to open this up. My keyboard's freezing. Alt, Control, Delete. There it is. And that. Open it back up again. There we go. Let's try again. So we have Fe2O3, and then if we were to balance this particular equation, we have a 3 here, a 2 here, which means we need a 4 in front of the Fe. Now, again, this is iron 3 oxide that's out here, and you and I also know iron 3 oxide is something else. Think about this now. You see it all the time. Any idea what iron 3 oxide is? Well, what happens to iron when it's exposed to oxygen? Well, it does, actually, like you observed. That's not what you normally observe, though. You just observed it right there. What do we normally observe when iron is exposed to oxygen? With the next 2 ingredients on your list there. What are the next 2 on that package?
Rust.
Yeah, this is rust. So what happens in here then is that when you open it up, that water and the salt in there actually causes that iron that's in there to rust. And it turns out rust is an exothermic process. We don't see that when it happens on our cars, but when we grind that iron up into really small particles actually, and we combine it with oxygen, we see it gives off heat. And we see that all the time when oxygen reacts with things. When we burn wood, when wood or gasoline combines with oxygen, we know that it gives off plenty of heat. Actually, anything that combines with oxygen is always going to be an exothermic process, but we don't think about it on our cars, but it is actually giving off heat as well. And so by grinding it up and getting a whole lot of surface area, we see that reaction. So anyhow, I like to bring that out even though it's not so much pertaining to solutions, just so you get some idea of what that is. So any questions on those packets there? Okay, then I'd like to look at solubility curves here. And we look at solubility curves. What this is showing here is the solubilities of a bunch of different substances. And we should probably define what solubility is. We define the solubility like this. We say that the solubility is the maximum amount of solute that may dissolve, or we can say that can be dissolved, in a specified amount of solvent at a given temperature. And again, if we look at this definition should look very similar to the definition that we gave for a saturated solution. So saturated solution is the solution. When we talk about the solubility, it is the amount of solute basically that it takes to become a saturated solution. So that would be another way to define it. Here's that the solubility is the amount of solute it takes to become a saturated solution. So we define it like this. And again, this is a 3-variable definition. And we can then wind up plotting the data something like this. And if you look at these graphs now and look at the axes on here, if I zoom this in a bit, on the vertical axis we have grams of solute per 100 grams of water. So this is the amount of solute per amount of solvent. So again, amount of solute per amount of solute per amount of solvent at a specified temperature, which is on the other axis down below here. Now if we look at this graph carefully, we see that there's a key on this graph. We have a key for gases, we have another one for solids. And if we look at this key, in general, let's see if I can get down to the axis here. I'll have to maybe zoom out one more level. There we go. So if we look at this key, in general, let's start with solids. What happens to solubilities of solids as we increase the temperature? So we increase the temperature, in general, what happens to the solubility of solids? Do they increase, decrease, or stay the same?
Increase.
Yeah, they increase. So we see every single solid line here except for one of them. The general trend is that as we increase the temperature, we increase the solubility. And then as a general rule for gases, as we increase the temperature, the solubility will tend to decrease. Okay, so again, for most solids, and again, that's a general rule, it's not the rule, there are some exceptions, but as a general rule, as we increase the temperature, the solubility of solids increases, the solubility of gases decreases as we increase the temperature. And the way we explain these is very simple. We explain them based on molecular motion. We explain the reason for each one of these on molecular motion. As we increase the temperature, what happens to molecular motion?
Increases.
It increases. So if we have a solid, we put it into water, the way that a solid is going to increase its molecular motion is to actually become aqueous. By becoming aqueous, then those particles can move faster. So it's more likely to dissolve than at higher temperatures. If we talk about gases that are dissolved, how does a dissolved gas become more mobile? It becomes more mobile by escaping into the gaseous phase. So as we increase the temperature, it can become more mobile if it leaves the aqueous phase and goes into the gaseous phase. So again, we explain each one of these trends based on molecular motion. Increasing the temperature increases molecular motion. Solids become more mobile by becoming dissolved. Gases become more mobile by becoming less dissolved and going into the gaseous phase. Now, some applications of these, and I'm skipping over some pieces that I'd normally cover in a fully seated class, but I do want to talk about the applications of some of these. One of the applications of this is if we look at dissolved oxygen. And of course, who or what depends on dissolved oxygen? Well, guess what? You and I depend on dissolved oxygen, because how do we get oxygen out to our fingers? We inhale it, and once we inhale it, the oxygen will dissolve in the water that's in our blood, and then that carries it out to other parts of our body. But fish for example, any forms of aquatic or marine life, well, not all forms of marine life, but for sure all aquatic life, will depend upon dissolved oxygen. Fish get dissolved oxygen into their bodies. And so if we look at a plot of dissolved oxygen, if we looked at the solubility on this axis here, and on this axis here, look at temperature in, let's say it's degrees Celsius, going from 0 to 100. We did this type of plot for dissolved oxygen. Now, again, oxygen is a gas at room temperature. Are we going to see the solubility go down, or are we going to see the solubility go up? What's going to happen? Is it going to go down like this, or is it going to go up? Which way do you think? We'll go back to our data here. What would our data suggest should happen to it? It should go down, exactly. So if we look at the plot of dissolved oxygen looks something like this. So the maximum solubility of oxygen sits at a temperature of 0 degrees Celsius. And in Minnesota, especially like long winters like we have right now, that's a good thing because, of course, in the fall, what happens is our lakes freeze over. They freeze over at a temperature of 0 degrees Celsius. It freezes over, and then we get the snow and whatever that's on top of it. And so most plant life in our lakes here in the winter gets killed off. Not all of it. There's some that remains behind. But most plant life gets killed off. And so basically, once the lakes freeze over, we're locking in the oxygen for the entire winter. And then those fish and other aquatic species there have to survive on whatever oxygen is locked in for the rest of the winter. And so the fact that we have this highest solubility at 0 degrees Celsius is a good thing. One of the other things we could mention here is something called thermal pollution. And this is probably something you've never heard of before. Normally when you think of pollution, you think of chemical pollution. But what would thermal suggest as far as pollution goes? Thermal would refer to heat. So this is actually heat pollution. This is not when we talk about global warming or climate change or anything. This is different. Thermal pollution is something that happens when we look at bodies of water. And one of the examples I can give is when I was an undergraduate student, I worked for an electric power plant, and this was down in Iowa on the Missouri River. And the electric power plants sat up on a hill, something like this, and then the Missouri River sat somewhere down below, down here. So here's the river, here's the electric power plant. Well, one of the things that all electric power plants do is they use enormous amounts of water. They take water in, that water is used to drive turbines and keep the equipment cool, and then it's returned back to the water. Well, now, if you think about then, if they're returning water back to the river and that water is warmed up, what is that going to do to the solubility of the oxygen? It's going to decrease it, exactly. It's going to decrease that oxygen. So now if you're returning water back to, say, a lake or a river or whatever else, and that temperature has gone up, again, the dissolved oxygen is going to go down, and what is that going to do to the survivability of species? It's going to drop that as well. So again, that's going to be something that's very critical. So again, when these power plants first went in, we weren't really aware of that type of stuff, so now we've had to kind of retrofit those things. And so coming out of this power plant, we have something that looks like this. And it's kind of these shelves that are curved up like this. And then coming out of here is going to be that water that's going to come down on these shelves. And the whole idea behind dropping this water down like this is to do what? Cool the temperature back down, exactly. And not only does it cool it down, but by churning it then and having these shelves like that, not only does it cool it down, But just like we saw with the iron powder there, we get more surface area. If we get more of that surface of the water exposed to the oxygen in the air, there's going to be more of the oxygen that can redissolve back into the water. But, you know, if you've ever been up to Monticello or whatever, or Big Lake even, in the middle of winter, you'll see that or if you go down to Red Wing on the Mississippi down there, you'll see where the water stays open all winter long because of the electric power plants are turning that warm water back into those bodies of water. But again, we try to combat that by cooling it down, aerating the water and such before it comes out. And I know I've driven by Moore Lake and Fridley sometimes, and I don't know if it's a year-round thing or if they only do it in the winter or some winters, but I've seen that they have a kind of aeration system in there to prevent the, I assume, fish kill from occurring there in the lake. And my guess is Moore Lake is probably a shallow lake, and if that gets frozen over, and it is shallow, yeah. I'm guessing, yeah. So I'm guessing then what the purpose of that whole thing is, and especially a winter like this where the ice has probably gotten really thick and covered for such a long period of time, if you have fish that are in there and you trap all the oxygen so it can't get in, those fish through a long winter are going to consume all that oxygen in there, and then they start dying. And of course then once the ice melts, then you wind up having all these dead fish and stinking the place up a whole lot. So I'm pretty sure that's what that's all about over there. But now, like when new developments go in and such, used to be that you just put in a development, you don't care about anything. I mean, relatively speaking, you don't care. We've become more aware of this whole thermal pollution things, and for example, a type of species that is very, very sensitive to temperature is trout. If you've ever been to a trout stream before, temperature of a trout stream is really, really cold. And when they would go ahead and put in the development and then put in a culvert or storm sewer that drain into these cold streams, that warm water would go in, and all of a sudden there'd be a bunch of trout that'd be belly up. There wouldn't be any chemical pollution per se in there, but just the warm water would cause the trout to die. So anyhow, that's some background information on why this stuff is important. Any questions that you have on this? All right. We can take a break or go straight through. Straight through? Get out early?